Hello, everyone. Welcome to episode 2 in the Set Theory for Non-Mathematicians series, where my friend Logos takes us through Charles C. Pinter's book, A Book of Set Theory. Today, we will introduce union, intersection, the universal class, and the empty class. One thing I would like to add, though, before we get started into today's material, is that the way that the episodes for this series will be working going forward is that every whole number episode will be going through new material within the Pinter book directly related to set theory. And then there will also be non-whole numbered episodes, such as episode 1.1, 2.1, 2.5, etc., which will either be introducing background ideas like the rules of logic, or going through a practice problem or two from the Pinter book. This is an easy way to differentiate between new material and review or sort of outside information that might be useful, but it isn't directly related to the book itself. So with that said, let's have Logos explain where we left off last time and then jump into the material for today.
Let's do a little bit of a recap, but only minor, especially if people are watching these back to back, because we ended with a recap on the last ones. Doing another big one will be annoying. The basic idea is we're going through set theory with an eye to philosophy, right? So there's the math part, and there's the why would a philosopher care about this part, because all this stuff shows up implicitly in arguments. Once we got past the intro and got into the meat of things, we first talked about using basically logic to build sets, with the idea that you explicitly, in some sense, describe what's in a set. So philosophers might want to talk about the people that are like Socrates in some vague sense, and set theorists get driven mad by that, because you have to have a pretty good idea of what like Socrates means and break it down into ands and ors and other truth functional operators in a sense. And this really comes to a head in this idea we see on the top left of the page, which is the axiom of class construction, the idea that you can build classes by describing all the x's such that some proposition is true of the x's. And if you remember from last time, it's important we're calling these things classes and not sets for now, because if you think about Russell's paradox, we have problems like the set of all sets that do not contain themselves as members. So if you have an unrestricted x on the left, and you have a really wild predicate thing on the right, this p of x, things break. But because we're talking about classes, we can always say that, hey, if something is an element of a class, I want to call it a set, not a class, and Russell's paradox is averted. But more importantly, philosophically, we are being very explicit about what's in our sets in ways that philosophers might shy away from, which is why you'll see some arguments talk about, say, pluralities instead of sets and things like that. We then talked a little bit about just how you can build sets, or classes, rather. If you've got big classes, you can take subclasses. And you can also talk about equality and subclasses using the other definition in terms of bigger than, which we talked about in the first video. I don't want to go over that again. But the idea is you're kind of carving up classes out of other classes to build classes. In this way, today we're going to be talking about more of that using more fine operators. So the first one is unions. Unions allow you to kind of take two classes and glue them together to make bigger classes. And the thing that really makes unions work is the idea that you don't count elements more than one time. So if one set or class has like 1, 2, 3, and another one has 3, 4, 5, then if you take their union, you get 1, 2, 3, 4, 5. You do not get 1, 2, 3, 3, 4, 5. And because of that implicit rule in unions, you can really just think of it as a straightforward gluing things together, so all the elements in either one occur one time. Appealing to Venn diagrams, it's basically this notion of, you've got the two circles inside the big, square of conversation, so to speak, right? And they have a little overlap in the middle. Exactly. Look at the figure 1 right there. That's it. That's a union, right? You've got A, you've got B. A union B is just all of it. Don't double count the middle. Count everything only once, if you're counting. Sorry, I teach statistics a lot, so the counting problem's a big deal. You just account for everything once, and that's your union. Intersections are a more fine way of talking about classes inside of other classes or sets inside of other sets, as we'll do later. Before we were just, looking at a naive case where it's just like, oh, something might just happen to be inside of something else or contain everything in something else but this or that. Intersections are a way that you can kind of make that work. So let's think about numbers. Let's think about dice. I love dice. I play a lot of role-playing games, and so dice are a really good example. So let's suppose I want a number that's both even and bigger than 16 or higher on a 20-sided dice, right? So you have 1 through 20 as possible rolls on your dice. The number's bigger than 16 or higher, 16, 17, 18, 19, 20. 5 numbers. What are the even numbers? 16, 18, 20. So you've gone from 20 numbers to 5 from your first condition, and you're taking that condition and you're intersecting it with another one, must be even, and so those 5 numbers become 3, 16, 18, 20. That's a good numerical way to visualize what's going on, and pictorially you can see it on the top right of the screen there with the Venn diagram. You get A, B, I only want the stuff in the middle, right? So A, think about as numbers 16 or higher, B is even numbers. Take the middle, what they both have in common, that's where you get 16, 18, 20. That's really, really important for playing games like 13 Age. 13 Age is like a role-playing game I've started playing recently, and there's these things called flexible dice that, you look at your dice roll when you roll your d20, and you get these cool benefits based on what you roll, and it's like really awesome. Anyway, so that's intersection. Intersections are a way of generating subclasses or subsets by imposing your own criteria. You kind of choose how you build them. I want all of these, but I want all of these that also follow this other rule right here. And we put them together, what do you get? That make sense?
Yeah, and for those of our viewers who have looked at or who have reviewed the primer on logic, which I think at this point will probably be a standalone episode, will notice the similarity to the or and rule in logic. The Venn diagrams all end up working out the same way.
Absolutely. There was one time I was teaching math and society a long time ago at college. And one of my students, because we were going over sets, and we were also going over logic, and there are 2 different kind of units in the class. And one of my students said, "Hey, these are kind of the same thing." And I'm like, they kind of are the same thing. Think about unions and intersections as and or operators. So ors and unions, ands and intersections. They're analogous. The big difference is that unions and intersections are over pluralities. So if we go back a page and we go back to the 1.12, right, that up there, you've got the ands and the ors going on inside on the right-hand side of the colon. That's the such that, right? That's the rule, right? So ands and ors determine rules. And on the left is talking about pluralities. So ands and ors usually are, operating on individual propositions or clauses or something in a statement. But in a set context, when you're operating on pluralities, I want everything that follows this and rule. Once you've added the everything, the plural, that's where you start getting into intersections and unions and things like that. That's the big difference. They're exactly identical, except you're ranging over lots of stuff in a class or lots of stuff in a set. Otherwise, they're the same.
All right, excellent. So then do we want to jump into the 2 defined types of classes? If that's the right terminology, I'm just referring to the universal and empty class, the classes that have their specific name introduced here in Chapter 1.
Yeah. I mean, this is pretty straightforward, and it should be. So the empty class is the class that has no elements at all. We use the 0 with a slash through it. The existence of the empty class is a consequence of the axiom of class construction. Indeed, A2 guarantees the existence of a class. By theorem 1.11. Sure, absolutely. So basically, let me interpret that gobbledygook. What they're basically saying is you can put any proposition that follows a logical structure, right, into your class to determine a class construction. So the question is, what if you put a contradiction in there? Well, if you put a contradiction in there, for what x's, wherever you get them from, for what x is a contradiction true. It's like going back to math, right? Suppose you try to solve an equation and you get like 0 equals 1 instead of getting x equals 4. For what x is the statement 0 equals 1 true? None. It's true for no x. So whenever you have any statement that's a contradiction inside of your class, set, whatever, that's basically just a fancy way of saying, hey, there's nothing in here, guys. And we just call that situation the empty set. Or the other class, the big one, that script U here is just saying that, what's a good way of putting this? The reason why I don't know how to put this nicely is because I'm used to ZFC set theory. So I'm going to kind of try to pause here and remind the reader what's going on. So in ZFC, you have like the axiom of specification. So when you build sets, you usually want to define the left-hand side of the curly brackets, right? I want to pull x from something in particular and give it a rule. And that's kind of one of the ways to get around Russell's paradox, because x can't be any set such that it doesn't contain itself as a member. It's got to be, a barber who lives in a town. It's got to be all the elements from some big set U that don't contain themselves as members or something like that. But the entire point of classes is we want to get around that, right? We want to allow the left-hand side to be unrestricted, because I just want to think about the set of all things like this cool rule, even if I don't know offhand, what category these things are coming from in the first place. So it's because of that, it's hard to motivate this script U thing. It's necessary for ZFC. There is no set of all sets in ZFC. You have to pull things out of somewhere. The most general thing we could think of is the universe of discourse. Let's just call it U. What we have here for 1.172 is it's like that. All we're saying is, hey, there is some script U such that any class would be a subset of that. So the way you'd construct that sort of thing is basically like a tautology, right? That's the easiest way of doing it. For what kinds of things are tautologies true? Well, all of them. And so if you leave this stuff inside unrestricted, I want all x such that tautology. Oh, well, there's no category that, wouldn't contain all these cool x's, so we're kind of done. So that's the way I think about it. The best way I can wrap my head around this, and there's probably a better one, is 1.171, the empty set. The empty set is built by cleverly using contradictions for our propositions inside of our curly brackets. And then 2, the curly U deal here is built using tautologies or things like it.
Is there anything else we want to say about, I'm looking down at the proof for 1.172. I mean, this is just saying, hey, imagine that we have an element of the class A, and then from that we can infer that X is an element, right? And because in order to be an element of a class, it has to be an element, and thus we can reason that this element is in the universal class, right? And so we can infer that for any element there will be a class that holds this.
Yeah, basically. I think if you already accept this idea of a universal class, then the proof for 2 that they have in the book is very, very straightforward, right? For any class A, there's going to be something in that class, because that's what classes do. They contain things, unless they're empty, right? So he's a non-empty class. Even if it's an empty class, technically, empty classes are also in everything from 1. But suppose you have a non-empty class. Well, there's something in it. And if there's something in it, then there's something in, the class of classes. The trick for U is actually, for 2. The trick for 2 is actually asking the question, where does this script U thing come from and why does it exist, right? So if script U thing exists, of course it's just going to contain any element that would be in any specified class. That's what script, curly U here is supposed to do. But where did it come from and how can we justify its existence in the first place is the bigger question. And that's why I wanted to talk about why we can kind of take its existence for granted. And the way I think about it is, tautologies. Once you put a tautology inside your proposition, for 1.12, you kind of just blow up and get everything, so to speak. And that's kind of like where your curly U comes from.
All right. Do we want to proceed then and introduce the next couple terms?
Yeah, sure. They're pretty simple. So if two classes have no elements, they are said to be disjoint. And that just means that if you try to take the intersection, they have no elements. You get a contradiction, basically. So here's an easy example. Let's go back to dice. Let's suppose I'm rolling a D20, playing D&D with the boys, right? And I want to roll a number that's both even and odd. Can I do it? No, I can't. Right? So if you think about all the even numbers on your D20, that's A. If you think about all the odd numbers on your D20, that's B. The intersection is just carving out a subset, or subclass rather, from what they all have in common in this case, which is nothing. And so you get the empty set. So what we say is all the even numbers on your D20 and all the odd numbers on your D20, those are disjoint. You can't find the commonalities to make a smaller subclass from them. And then from that, we can get the idea of complements. So complements are, well, what they say is a complement is the class of all the elements which do not belong to A. Let's turn the page. So in symbols, they give us some symbolization for that. They use this cool little prime. I've seen like a C on top. I've seen a caret sign on top, like in your calculator. I've seen, the dash scene they got going on here. It's my favorite one. So basically, the idea here is I'm looking for everything not this. And you can see the picture of that in figure 2. On the right side of the page, you see kind of the square, you see A, and you see everything around A. That's basically the complement of A. That's what's going on. So in practical terms, let's use the D20 example again, because I just love RPGs, right? If I know that I need to roll a 12 or higher to hit, then when is my miss, right? When do I miss? The miss would be the complement of that. It would be everything from 1 to 11. If I roll a 1 to 11, I miss. If I roll a 12 to 20, I hit. Those two are mutually complements. And so this idea of carving things up, everything in here and not in there and vice versa, very, very applicable. That's basically all there is to it. I don't know if there's anything else I really want to say about that. I mean, there's not too much going on here. One thing I will say is notice the parallel to Russell's argument, like Russell's paradox from the intro for our first video, right? I want all the x such that x is not an element of itself. Think about that using complement notation. And that's why the paradox gets so wacky. So what's going on here is we're using this A thing to help us out. I want all the x such that x isn't in A, and that's how I can think about figure 2, right? So you have everything in A, everything not in A, and there you go, that's your complement. But what if instead of the big A there, you had the x? How would you even visualize that in terms of like the Venn diagram and things like that? That's what makes Russell's paradox so weird and wacky. And this is why it's really, really important to have some kind of restrictions either to the left of the colon or to the right of it somehow that kind of make it make sense and workable. And complements are a nice way of doing that. So long as you're talking about, what's restricted here, you can always get the cool little visual picture. But these things are super, super useful in math and all sorts of other topics. And stats, too. This is a really big deal. One of the most useful rules in probability, it's so basic, is the idea that if you add up all the disjoint, right, so there's no overlapping, all the disjoint events and all their probabilities, they should add up to 1, right? Because they're all disjoint, they should take up the entire sample space, right? Assuming you've got everything. And so you can use the complement rule, where if you want to find the probability of, let's say you have two disjoint events, A and B, in your sample space. The probability of one of them is 1 minus the probability of the other one. And that's a big deal because there might be some things that are really, really hard to count. You see this like binomial distributions and things like that all the time. And what you can do is you can kind of reword your thing to say, look, instead of trying to count up all these things and add them up and get a probability this way, what if I look at everything they're not, which is, these few things over here? Well, 1 minus what they're not gives me what they are, basically. I mean, that sounds kind of crazy, right? There's a lot of negation there. Let's say that again. 1 minus what these things are not gets me the probability of what I want, what these things are. And that trick we play all the time. Philosophically, I don't know that, again, unions, intersections, complements, I mean, those aren't really big things that, philosophical arguments have a huge stake over and things like that. It's just like baseline stuff that people kind of assume when you're talking about these things.
All right, so that concludes episode 2 in the set theory series. In the next episode, we will be introducing ordered pairs and Cartesian products, and we wanted to spend a whole episode dedicated to those ideas. In between episode 2 and 3, episode 2.1 will air, in which I will go through some of the exercises in the book and show how we can apply some of the ideas that we've been learning. And with that said, I hope you enjoyed, and see you next time.